Okay, so in this video, I'm gonna show you an example where we can solve logistic regression by Newton's methods. Okay, so remember the logistic regression, we have the regression function as the y equals to the s times x with w. Okay, where this you can think of each observation is like this one, where the s is logistical transformation, which is given by 1 over 1 plus e to the power negative t, right? So this logistic function is a function of t. Okay, and the derivatives of this transformation is given by remember, you take the quotient rule. Actually, we solved this last time. I won't repeat again here. So you can practice. So it's t st times 1 minus st. Okay. So to solve the Newton's method, we need to solve the gradient first. So gradient of the cost function. So the cost function, remember, the cost function is just the sum. The cost function is recall the cost function is equals to negative summation. If you check last lecture notes, it's I from 1 to n yi times natural log siw. Sorry. Natural log si. Let's use a simple notation si. Okay. Plus 1 minus yi natural log 1 minus si. Okay, so where this si denotes the logistic transformation of the xi times w. Okay, and in last class we talked about how to find the gradient, right? Last class, do you remember, if you recall, last class we derived the gradient descent algorithms for logistic regression. So this is logistic regression. Yeah, this is the cost function, and this is the gradient. So we solved the gradient function here. Maybe we just use the same formula for the gradient. So the gradient will equals to negative summation I from 1 to n yi minus si xi, which equals to negative. We can use the matrix notation. So x transformation, design matrix transformation times y minus s. Okay, where this s is just a vector of the s1, sn. Okay, so this is a gradient of the cost function. Because now we need the second derivative, because if we apply the Newton's method, we need not only the gradient, we also need the second derivative, Hessian matrix. So now let's solve for the Hessian matrix. So this equals to, okay, actually the derivative, the second derivative, you're gonna need to find the derivative of this term with respect to the w again. And actually, which term has yi, there's no w inside, xi, there's no w inside. So there's only w here. So we only need to find the derivative of the s respect to w. So actually, and this yi and xi are constants. Actually, we are looking for you can think it's derivative yi, xi, negative, minus plus. So plus second si, xi. Okay, and so this term is constant, so derivative disappeared. So the only derivative inside is this here. So we have the derivative si. Recall the formula for derivative si is s times 1 minus s. So this will be si 1 minus si, and then times xi. But both term si has the xi, so when you take a derivative, you apply chain rule. Actually, the formula will be xi transform too. And then you apply this to every term, so I from 1 to n. And actually, this has a matrix form, so it can be written as design matrix x times a diagonal matrix and then x, where this, recall this diagonal matrix is just the si 1 minus si 1 s1 s1 sn 1 minus sn. Okay. Actually, one property is this omega matrix is positive definite. Because each si times 1 minus si will be greater than 0 for all I. Okay, so one good property is if this matrix is quadratic term is positive definite. Recall in last the lecture we talked about the quadratic forms, right? If this quadratic form, the matrix is positive definite, this means this second derivative is positive. Second derivative is positive, which means the cost function is convex. So therefore, we get another remark here is logistic regression always have the global optimum point. So the logistic function, logistic regression, cost function is convex. So Newton's methods. So there will be a unique global optimum point. So can be found by Newton's methods. So in other words, Newton's methods for solving the logistic regression, you can initial a parameter with 0 vectors. Initial Second, repeat until converge. So you solve for the gradient, right? Solve for the Hissing matrix. Hissing matrix can be solved by solving this linear system. So linear system is given by x e multiply x y minus s. Okay, and then you update w by w plus this e. Okay, which means you just solve the second derivative of this part, and then you update this. So this is a Newton's algorithm for solving logistic regression. Logistic regression.